Good afternoon. Today we will see some belongs to our textbook chapter 5 and 6. Okay. Today we are going to finish our chapter 5. The topic is convolutional neural network, and we will go into some recognition topics such as image classification. This is the last slide we see in our previous week. It is the deconvolution approach. It means given an input image, given an input image, and we will go through the network by several different layers. So there are some fundamental functions. First, it is a convolution. Then we will use maximum pooling to select the largest activations. Then through a ReLU, then we will go to the next convolution and activation function. So Zeller and Fergus, they invent the idea. Once they can record the positions of those maxima pooling layers, then once they get the activation value, they can use those activation value and go back to the unpooling layer and invert the activation value and then reconstruct the signals which will activate a certain neurons. Okay. So here, see this map. This map is where they record the pooled values. And then here they use the deconvolution or the transpose convolution to reconstruct the input image or input signals. So, they show their results on AlexNet. Suppose they have a structure of AlexNet and train the AlexNet on ImageNet dataset. There are 1,000 classes, and once the network is trained, they fix those weights. Then they use those weights to see what is the important patterns or signals which will activate those neurons. So, let's see. In the AlexNet, there are totally 8 layers. This is first, second, third, fourth, and fifth. Here, we can still see the spatial relationship because all of those layers will generate the feature maps. They still preserve their spatial relationship. But in the latest 3 layers, they use multi-layer perceptrons, which no longer preserve their spatial relationship. So let's see. In the first layer, see here, how to generate activation values in the first layer. We use the 3 convolutional kernel 11 by 11, and then there are 3 channels. So this is only a convolution step. So let's see. Because this kernel size is 11 by 11, so when they try to pick up some large activation values in the first layer, they will generate the 11 by 11 patches. So this example, when they pick up the 9 largest activation values in the first layer, and then they use their method, this one, to reconstruct the input signal, they will get these 9 patterns. What are they? So from the first, second, fifth, ninth, and 7th, you can see they are very obvious edges. And from this one and this one, the change of intensity is not so obvious, but you still can see there is a pattern, the change of colors from one side to another side. Okay. That is also a kind of edge. Okay, this is the result generated by their inverse network, and they can search those test or validation set. What kind of patches will generate the largest activation values? So for the first patch, they find those patches will generate the largest field. Similarly, for the second one, and they will find those real-world patches will generate the largest activations. So it shows in the first layer, the network look at or pay attention to edges. And let's see in the second layer, okay, as you can see, the patch size becomes larger in the second layer. The reason is, okay, in the second layer, in addition to the convolution, there is a maxima pooling, and there is another convolution. Therefore, if you want to, how to say, a neutron in the second layer, it will has a larger perceptive field. Okay. Therefore, you can see the patch size is also become larger. Okay. So this is the 16 highest neuron activations in the second layer, and in their corresponding patches in the real-world images are at the right-hand side. Okay, so in the second layer, what does the neural world or what does the ethnic snake look at? Certain texture. Okay. Compared with the first layer, it sees edges. And in the third layer, okay, as long as the perception field becomes larger, the network see more textures or patterns in the third layer. So therefore, you can see in the third layer, some neutrons will focus on human faces, and some neurons will focus on the grid patterns. And on the fourth layer, okay, as the perception field becomes greater, okay, some shape or structures occur. For example, the neuron of this, actually the patterns will activate as this neuron is what is that? Dog's face or dog's faces. And the patterns will activate these neurons will be what? The structure, something like a bird's feet. Okay. And for this one, okay, this is difficult to tell because it is a mixture of several patterns. But as we can see, it will cover 2 or 1 vertical edges, and some, at top of the 2 vertical edges, there are horizontal edge. Okay. Oh, on the 5th layer, the latest layer, we can observe the shape. Okay, so we can see here, as you can see, it captured the shape like some olive. In addition to human faces, but the tires are also included. And here it captured the shape of wheels, some shape of a circle. And here it captured the structure of something like eyes. And this, you can see the dog's faces. This is also the same. Okay. Okay, so in their paper, they also do another interesting experiment. That is, so usually we will use an input image, okay, go through the network and to predict its result. But however, if they use a gray square to cover the input image, then what will be the result? They use this method to test what is the most important neuron in certain layer so that the network can detect what is the clue or factors the neural network will recognize, oh, this is a certain object of this image. Okay, for this example, there is a Pomeranian, a breed of dog in this image. Okay, so what is the meaning of the second column? It means this is the okay. So there are. Let's take a break of this layer 5. In AlexNet, there are 256 channels in layer 5, and among the 250 layers, also channels, they pick up the one have the largest activation values respect to this input image, right? And they all, okay, so they move the gray squares from the left top corner to the right bottom corner. Okay, great. Then they record the strongest activations of that channel. So if the gray square blocked a certain region, okay, and then the largest activation value keeps the same. What does this mean? It means the gray square doesn't affect all the largest value. So as you can see, when the block will affect the largest activation value, it happens when the block moves somewhere close to the dog's face. Okay. Therefore, the red color means it's a high value, and the blue color means a low value. As you can see, this is a color bar, okay, from 1.0 to 0.0. Okay. So what does it mean? It means how does AlexNet recognize this image is belongs to the Pomeranian? It means it uses this region, the faces of the dog, to recognize the image. Okay, so this is the reconstruct image using their method. This one, okay. So they've used the largest neuron value, activation value to reconstruct the image. They get this. So what is this? This is a shape of this region, okay? The left eye and the fur here. And the other 3 blocks are the same neutron, but they use different images to try which image will generate the largest activations, okay? When they found those images, they used the same reconstruction method to generate the signals. So they will look like this. And they try another, they report another result. It means when they move the gray squares from a pixel by pixel, then how will the location affect the predicted probability? So it means when the block is placed at the left part corner, it doesn't matter. The AlexNet neural network still recognize this is an image of Pomeranian, but if they move the gray squares to cover the face of the Pomeranian, then the probability AlexNet think this is Pomeranian drop dramatically. It also shows the senses. The face of the Pomeranian dog is very important for the AlexNet. Okay, so they also report another experiment result. It means when they move the gray square from one pixel to another pixel, what will be the class or classes AlexNet predicted? Okay, it's similar like this one. So it means, for example, this is the place unimportant. Therefore, when they place the gray squares here, then AlexNet still think, okay, this is the image of a Pomeranian. But when they move the grayscales to cover the face of the dog, okay, they will see, this is the image of tennis ball. Why is it tennis ball? Because if they cover this region, then there is a tennis ball. That's correct. But however, if they move the gray square to cover partial of the tennis ball and partial of the dog's face, what will the AlexNet think? It think, okay, it may be the Chih-Yuan, another type of dog. Okay. Or it is the image of Pekingese, also another of type. Why? Because if you take a look of the three breeds of dog, their fur or their shape looks quite similar. So this is the example image of Chih-Yuan, and this is another example image for Pekingese. Okay, so let's take another look. Here, the true label is car wheel, so this is the wheel. Okay, but however, if they use the same method to cover certain I should say, however, in the layer 5, when they pick up the layer with the largest activations, all right, okay, the message collected by the neutral is not wheel. In fact, it is not the label or logo of the racer's car. Therefore, as you can see, if they move the grayscale to cover the label of certain brands, okay, the activation value drops significantly. So when they use their reconstruction method to reconstruct the pages, okay, you can find it. So what is this? ADAC, okay? That is a certain type of logo, okay? This is said PO something where, and the GRE, and this is a Chinese master wing, okay? So the same, what is signals is collected by the neutral, certain logo. Okay. And but however, when they do this experiment to see what is the region will affect the result of predicting the image as a car wheel, yes, okay, we can see when they cover this region, okay, the AlexNet neural network will not predict this image as a car wheel. So it means, yes, this region, the wheel of the car, is the important or key information for AlexNet to see whether it is a wheel. Okay, so this is, again, if they remove certain region of information, okay, AlexNet will think, oh, this is a racer, a cab, or a police van. What are they? All of them are certain of vehicles. Okay, so that's the method to visualize AlexNet. And AlexNet is the winner of the 2012 Internet challenge. In 2 years later, there's another winner, that is the Google Net. And first, I show the, yes.
Ask a question about, say the layer 5 or layer 4 slide. The activations are basically identical to the training set, right? Like, I think if you go back to slide 5 or 4.
This one?
Like layer 5 or 4.
Layer 5 or 4. Yes, this one.
Sorry, forward a few slides, but you can see the examples next to the activation.
This one? Okay, okay.
Yeah, this one.
Okay, okay. Yeah.
You see that the activation,
so
the feature map is identical, basically identical to training samples, right? So the pattern in the top left is almost identical to the whatever object that is in the top left. So the network is learning very, very specific feature maps, right?
Yes.
Which seems like a bad thing, right? In
Yeah.
the sense that you want your networks to be general.
That's right.
Be able to go outside of your training data.
Yes.
So, I don't know, is that the case? Is this bad, or how do we think about that?
Okay, okay. There is okay, I should say, okay, some people found, yes, neural network may not be well generalized. They just memorize those examples. So this is the first find, I should say, their observation. Okay, and the second explanation is why there are a lot of training images. Okay. Why a neural network, for example, AlexNet, can generate, I should say, generate the correct class labels. Okay, because neural network is a contract machine. It means in the input space, they will, through the optimization, they will contract those examples to divide the input space into many, many small subspaces so that they can generate a certain, I should say, correct labels. However, if our test image or validated image is slightly different or shifted from input space to another input space, it will be misclassified. So that's my explanation. Okay. All right. So So this is another network called Google Net. Okay, so here again, AV layer has its own label from 2D 0, 3A, 3B to 5B. Okay, and within each inception, so within this region, this is a structure called inception layer. So from previous layer, it will use several one-by-one convolutions to reduce the number of layers. And they will concatenate together, become a new set of feature maps. And this network is developed by Google, and those researchers at Google, they also are interested in why or how the network look at those input images. So there is a paper. It is published online. Okay, it's not a physical paper, not in any conference, but you can find it online. So they developed a method. It's called okay, I should say, unlike unlike zero and focus method, they try to remember the position of maxima pooling. Okay. So they treat the input, they treat the network as a function. It means given an input image or some input data Then through those layer by layer, they will generate activations at a certain layer or certain layer, so this is a certain neuron, this is a certain layer, and a certain channel, and a layer consists of several layers. Okay, and even more, those layers will contribute to the class logic, and finally through the softmax layer, they will generate the class probability. So they treat input data to certain neutron or certain unit. They can treat it as a function of the input data. Therefore, since it's a function and it's a differentiable, so they can find the gradient of those input data, so that following the gradient to increase the activations of the certain unit, okay, they can reconstruct, or should say, they can create some images which will maximize or create a very large activations for those units. So this is an example. If they want to see what kind of image will create the very large activation of a certain channel, okay, they in the beginning use some random noise. Then following the direction of gradient, okay, they change the values of the input image. Then after the step 4, they generate this image. Step 48, they generate this image, and after 2,000 steps, they generate the image. So this image means it is not a realistic, I should say, it is not a real world image, but it will generate a very, very large activation value for the mix 4A unit. So mix 4A is here, okay, and there are several layers. It's 11 layer. Use this method, they can generate images for a neutron, so like this one, for a channel, so like this one, and for a layer, okay, it looks like this one. So this is the result for a certain logic, and this is for certain probability. Okay, so compare the two differences. In Zeller and Fergus method, okay, as you can see, this is the they can only reconstruct the signals, but in Google Net, they can reconstruct an image. Okay. So for us, image is more intuitive than those signals. So let's go through the layer by layer. Okay, we can see something similar. In their low-level layer like this one, they found, okay, the result is similar as the Alexander. For the early layers, what do they pay attention to? Age. And in the second layer or middle layer, so this, as you can see, this is 2D0. It is very early. It's here. And the 3A is here. Okay. So in the 3A layer, they see something like a texture, but it is a fundamental layer of texture. And in the 4A layer, they see advanced texture. They are more contrasted and more structured pattern there. And in the 4B and the 4C layer, they started to see parts. So you can see there are some structures. Then in the 4D and the 4E layer, they started to see objects. So what is it? As you see this image, it looks like a structure or a building. And in this image, you see the part of, it looks like some body part. Okay, so here, Oh, okay. This is the adversarial example. It is shown in our textbook. And here also, this is related to Ji's question. So let me first explain what it is. So we have the AlexNet, and okay, and when we train the AlexNet on ImageNet, there are 1,000 classes. Okay, so some of them. Okay, so this is a bus, and okay, this is a breed of dog. However, okay, yes, when we use these images, the AlexNet will tell us the correct class labels. But however, if we add a little perturbation or differences into this image, so this is the combined image. It is just the input image plus the alternation signals. Then 1, 2, 3, 4, 5, 6. All of the 6 images will be recognized as a ostrich. Okay. So why it happens? The reason, just as the question Jia added, because AlexNet is the contrast machine. It learns or split the input spaces into many tiny small pieces of spaces. So, okay, for the 1,000 classes, yes, it can be recognized using those training data. But however, between the boundaries of those classes, if you just slightly shift the training pixels in a input space, okay, the data may fall into another spaces, so it will be recognized as this ostrich. So this is the adversarial examples, and many interesting researches are based on this topic. So we can see this is example. So this is a common stop sign. Okay, and this graffiti. The 2 researchers of this paper, they try to develop an algorithm, so it will mimic the real-world graffiti. But so this is their result. Okay, so their algorithm will collect many images to create a distribution. Then their algorithm will develop what is the alternation they can add into a certain image, so that the neural network will think, okay, this is not a stop sign, but a speed limitation sign. And again, so let's see this again. What's this? This is Ji's homework 1 topic. This is a very new paper. It's a CPR 24 paper. Okay. So again, this is also a adversarial attack. Let me explain this image. Okay, so these are 2 synthesized images. What do they want to do? There are some existing depth estimation method to estimate the depth of this image. Okay, so here is closer to the camera, so the depth is shorter. And here the far away background the depth is greater. Okay, and use a certain pattern placed on the center of the image. Then they will destroy the detected result of those estimation depth estimation method. So in their paper, they test 4 different depth estimation methods. So the mono depth 2, depth hints, many depths, and the robust depths. Okay, they found all of the 4 depth estimation algorithms will fail. Okay. However, if they just use those patterns on the render those patterns on the 3D object, it doesn't work. Okay, so they want to develop a new algorithm which will work if the patterns was rendered on the 3D objects on the car. So this is their result. When they use the apply their method to this result, okay, the car they should get the correct. I should say those 4 depth estimation algorithms should generate the correct depth result like this one, but all of them fails. So this means their adversarial attack algorithm succeed. All right. Now we are going to talk about what is self-supervised learning. Okay. So let me recall. When we use AlexNet, every training image has a label. It means what the class it is. But what will happen if there is no labels? Okay. So how do you convert a dataset without a label, but you still can develop a method to learn something from those data? So that is called self-supervised learning. And let's see some examples. So first, there is a famous paper. When you search self-supervised learning, you often will see this paper. Okay, so this paper means given image, so there is no label, but from the image you can crop certain regions or patch. For example, this one, given this region, you can crop 8 regions by their direction. So there's 1, 2, 3, 4, 5, 6, 7. Therefore, you can create training data. It contains a pair of patches. So this is X input data, a patch and its neighbor patch, and also Y. Y is the label, the direction from the second patch to the first patch. So this is 3. It means this patch is cropped from here. Okay. So in the beginning we have no label, but here we create our own label from the input image. So if we can develop an algorithm to learn the labels, then we can use it to, for example, for this one, what does it look like? It looks like the part of a bus. Okay, so certain route expressed, and what is this part? It looks like the body of a bus. Therefore, if we can train an algorithm to predict it, then we may see we will predict the label might be 8. Okay, and here what is this? This looks a part of train, and what is this? This is the top of a train, because you can see some electrical core here. Okay, so from the pair of input image, we may predict the label might be 2. Okay, so let's take a look of, yes, they developed such an algorithm. They use AlexNet to do it, right? So how do they do? So let's talk. So here, from an input patch, the convolution 1 pulling 1, convolution 2 pulling 2, and 3, 4, 5, and so there are totally 8 layers. They follow the same architecture of AlexNet. And here you can see this LORN. It stands for Local Response Normalization. It is normalization method used in AlexNet. So they exactly follow the AlexNet. But however, their modification? as you can see, the dashed line here means they share. Okay, the two networks share the same weight. And in AlexNet, from fully connected 6 to fully connected 7, it's a multi-layer perceptron, or fully connected layer. Here, there are 4K neutrals, and here are 4K neutrals. Because it is a fully connected, it can be combined into a new layer. So here, this is the fully connected 7, right? So they collect a lot of training samples and their labels to train the network. So they can generate a correct, I should say, in AlexNet, okay, it will generate 1,000 logit. Here, they only need to generate 8 logit because there are only 8 classes in their training data. Okay, once the network was trained, what can they do? Okay, given an image like this one, they can crop a certain patches from it. And here, there are, say, 12 patches. Use their method. They can reconstruct certain images like this one. They can recover the layout. So let's see another similar but slightly different self-supervised example. It means, given an image, the same, okay, in the previous one, it only predicts one direction. But in this method, given an image, they will crop 9 patches. They will slightly change the location of the 9 patches, okay, and they will create a puzzle. They want to develop the algorithm can automatically reconstruct or solve the puzzle like this one. When do you have a toy when you was a child? You can move the block from one place to another. Then finally you will reconstruct the image just like that. Okay. All right. So how do they do? Oh, okay. I should say this is also a self-supervised problem because in the source image, do we have any label? No. Okay. But we can create the puzzle. And do we know the answer? Yes, because we created the puzzle from the source input image. So we know the answer. Here, we have the input and we have the answer. So we can create a supervised learning algorithm or method to learn it.
How do they create the puzzle? Because that one looks very perfect. It's like got the tiger's head and it follows the body. Do they just randomly place the 9 blocks, or are they?
No, in fact, they don't randomly, partial randomly, but not total randomly. Okay, so let me take a look. Well, here, when you see the head of the tiger, right, and this is the neck of the tiger, they will prevent the neck at the bottom of the head. Okay, so let's see the next slide, and let's see what. Okay, so that when they crop the 9 blocks, yes.
But how do they get the fields where to crop?
Do you mean where to? Okay.
Yeah. Do they manually draw the boxes, or is it like an algorithm that says here's the box?
Okay. First, given an image, they randomly select the region they want to crop. So like this one, the large here. And they, however, for every single block, they will slightly give a random number to shift its location. Okay. So that they will not overlap, but they will not well aligned. So that's the reason you see some gaps are slightly larger and some are small. Okay. So how do they do it? Let me take a look. Let's take a look at the method. So given a 9 blocks, in fact, there are only 64 acceptable permutations. Okay. Why? Because here they don't, for example, if this is the part, they doesn't allow this patch will be placed here because the two in the original image, the two are adjacent. So they don't allow the two patches will be adjacent in the puzzle. Okay, so therefore there are only 64 accepted permutation. Okay, so what do they learn? They learn a network. In fact, it is also okay. So the network will generate the prediction of 64 classes. So okay, then once they can collect a lot of training images to train the network, so that they can, given any puzzle, use their network to predict which permutation of the 64 is. So here, okay, if this is the index 34, that is their permutation. Once they can get the permutation index, they can use a table to know, okay, which the permutation is. They can reconstruct the location of the 9 patches to get the correct answer. Okay, so let's see one more example of self-supervised learning. It's automatic colorization. It means, given a grayscale image, it will automatically colorize the input image as a colorful image. Okay? So why is this a self-supervised learning method? Because suppose we have a lot of training image in a colorful. Okay, we can easily create the grayscale one. Therefore, we have a lot of paired training images: the colorful and the grayscale. Okay? So there's no label, fine, no problem. Once we have the paired training data, grayscale and color image, then they create a network to learn from the grayscale to predict the A and B channel. So that they can reconstruct the L star, A star, B star color space and use images in the space to convert it to RGB space. Okay, so they can get the colorful image. Okay, let's see some result. For this color, okay, this means the good result. This is the ground truth, and this is their reconstructed image. When you see the color of the water, the reconstructed might be better. But when you see this is this color is their poorest result. So this is the ground truth. It makes sense, and this car it looks old. And something wrong. Okay, the same. Okay, here Dino. Okay. Also, this is a Jai's homework too. It is also a self-supervised learning method. So, okay. So let's explain why it is supervised. First, see this title: self-supervised vision transform. It means okay, it is self-supervised method, and it uses vision transformer, right? Okay, so why is it self-supervised? So let's take a look. The X means input image, and then they use the same input image to create two generated image, X1, X2, because X1 and X2 are generated from the same image, so they should share the same class label, or they belong to the same class somewhere else. Okay, so therefore their probability of those classes should be the same or should be similar. So here in their training data, there is no label, but they use this method. This design. They create a way to learn a pair of images. They should be the same, so it becomes a self-supervised learning method. All right, any question? No? Okay, let's take a break. Okay, now we are going to our chapter 6. Chapter 6 is a recognition, and there are three sections. It is image classification, detection, and segmentation. So we are going to talk about image classification today. And in the beginning, okay, our authors explain what is recognition and what is the simplest recognition. So this is an example of instance recognition. So what is instance recognition? It means, see, this is a toy train and this is a toy flag. Can you find them in this image? Okay, so it means find the exact instance in the image. So of course the answer is here. Here you can see the frog's head and the frog's foot. And here you can see the first toy train. It is blocked by a book. And this is another toy train. It is partially obscured. Okay. So it means find the instance in the image. Okay, and this is another relatively difficult, challenging task. It means class recognition. It means you need to find all instances belong to the same class. Okay, cat, cars, and bicycle, etc. Okay. Also here, let's explain how do they find the instance in the image. Okay. First, if you want to find it, you need some key point or features. How to find a good key point? So let's see three examples. And let's see, suppose this is an image. And here, this is the two edges. So the cross of two edges become a corner. And if you have two images, the red one and the yellow one, then if you have use a key edge as a key point, well, it is good because they are rare, and you can find them in another image relatively easy. However, if you use edge as a key point, then there's a problem. It means even for this edge, and you are looking for similar edges in another image, you will find many candidates. The same, if you use a smooth region as a key point, there's another problem. You will find many similar smooth regions in another image. Okay, so let's take an example here. So the left image and the right image are two different images. If you are going to find something like this, okay, this is a patch of a corner. Oh yes, you can in the target image find, okay, this is something like your corner patch from your source image because they are rare. So maybe they are just unique in the target image. But if you use the edge patch as your key point, like this one, then the problem is there are many similar edges in the target image. If you use the smooth region as your key point, then there will be a problem. So there are many similar patches in the target image. Okay, so the next question is how to find the corners in the source image. So one of the famous methods called shift. Shift is shift invariance. Okay, okay, here. A scale invariant feature transform. So how the first step of the shift is to find the edge, a corner in the image. How can it achieve the scale invariance feature? because it creates not a single one, but a set of images. So, okay, suppose this is the input image. This is this one. Okay, then it will apply different Gaussian filters to gradually blur out the image. So this is most clear, and this is slightly blurred, and this is more blurred, and there are several layers. Okay, so the set of layers is called an octave, and they can subsample the image. They will generate another octave like this one, and in the second octave, it will also apply Gaussian filter to generate different layers. So within each octave, it is a pyramid of Gaussian filter, and they divided one layer by subtract one layer with another layer. They will get the difference of Gaussians. So, and they find the maximum value or minimum value in the difference of Gaussians. So how do they do? They compare a pixel with its neighboring 26 pixels. So once they found the minimum or maximum value, it is possible it is the edge value. So they will further check whether it is an edge and corner or a smooth value. So how do they do? They will check the gradient of that pixel. If it is a edge, usually there is a large gradient for one direction and the large gradient for negative large gradient for another direction. So it makes it an edge. If it found this edge value, discard it. It won't use it. The same, if the gradient of the pixel is very small, it usually means it is a smooth region. Therefore, disregard it too. So here, as we can see, because it needs to compare with its 26 neighbors, so for the first layer or the lattice layer, there's no neighbors at the top or the bottom, so it won't find the maximum or minimum value there. Okay, once they found those key points, they will use the histogram of gradient to create the feature. So what is the histogram of gradient? It means for a pixel or for a location at the center, there were some nearby pixels. For example, there are 8 by 8 nearby pixels. Then within the region, every pixel has its own gradient. They can extract the gradients from those 60 pixels and create its angle of histogram. Suppose they only use 8 different directions. It means like this 8, and then they will accumulate those intensity, magnitude of those gradients. So they will generate one. And for every 4 by 4 region, they can create a histogram of gradient. Then it will become a descriptor or feature vectors for a location. Okay, so this is illustration. And in law is the last name of this method's inventor. He is a professor at a University of Canada. Sorry, I forgot the name of the university. Okay, in Law's method, it uses a patch size of 16 by 16. Okay, and for each region, it will create a histogram of gradient, and within the gradient there are 8 values. Therefore, the total length of this region will be 16 because there are 16 blocks. In each block, there are 8 values. So the feature length of this feature of this shift feature will be 128. Okay, once they get the feature, they can be used to match similar features in the target image. So for example, what is the book? This is the first edition of our textbook. So you can see the author is still Richard Selesky, okay, and the computer vision algorithm and application. Okay, so suppose we have a pair of images. One is this one, and another is one. We can extract a lot of key points and extract their shift feature, and then we can match. Thus, we can find, okay, this point, it is likely to be this one, and this point will be likely to this one. Okay, so they can, once they can match the two images, they can create an application like this. Given an image taken by a photographer or a person, and the image is taken by another person, they can match whether the two images are from the same objects. Okay. And once they can apply the method for a large-scale data set, okay, they can create something called image retrieval. Given an image, they can use the matching function to go through all of their images in their data set and then retrieve the ones which satisfy certain criteria of this matching point. But here, let me explain. As you can see, this is a rectangle, right? But here, what you see is a lot of points. They are not using the same method. And here, but however, when I check our textbook, I cannot find the images like this one. So I use another image. Okay, it is also the image in chapter 7 because it talks about the image matching. Okay. All right. Okay. Yes, please.
In the SIFT example, there's some lines which are red, which are presumably saying it doesn't match, or it's not where it's expected to be. Is it because it learns like a transformation function and then if it doesn't follow that, it goes red? Or?
Yeah. Okay, so here, okay, we talked about that we can match that, but we didn't talk about how do we match that, right? Okay, so there are many methods to how to match that. Okay, so as far as I know, the one mentioned in our textbook is the ransack. It means randomly pick up a certain key points and search the candidate one in the target. Okay, and then try to find the maximum probability to matching a set of key points to another set of key points. And here, so if you can, I believe there are many. For example, this is A, right? And you can see the corner here. But and there is A. But however, they cannot find. I should say there are two key points there, but they cannot be matched. So they are not drawn on this image. Okay, so right. So now let's talk about the image classification topic. So this topic has been studied for a long time. In 2006, okay, there is a paper. They try to address the image classification problem. And the researchers from this paper are from Xerox. Therefore, they propose a data set called Xerox 10. There are only 10 classes within the data set. So you can see that bike, book, chair, phone, shoe, boat, car, flower, road sign, and soft toys. Okay, here. Let's go back to the definition of instance recognition. Here, okay, so here this example. If we are going to do class recognition, it means for those images. They all belong to the same class. All of them are bike. All of them are books. So, as you can see, this is a more challenging question because we are not looking for a specific shape or key points. We need to find some common feature shared by all those images. So, okay, so there are some, before neural networks, there are some existing methods, and there are some challenges addressing this problem. So the most one of the famous one is the Pascal VOC. VOC stands for Visual Object Categorized Challenge. So it holds for 8 years. Okay, in the beginning, there are only 4 classes and 1,500 images. In the next year, it extended to 10 classes, and as you can see, they increased the classes until 20 classes, but they continually expanded the dataset from 15K to around 10K and more images. Okay, so let's see some examples. So here, this is their classification task. Given this image, they need to clarify this is a chair, bike. So both of them are bike. Okay, and there is a cat. Another is a dog. Okay, and this is the bird or duck, something else. And it's a boat, right? And in addition to classification, they also have the segmentation challenge. It means, given an image, how can you develop an algorithm to recognize or segment chairs from the image? And there is another object. I think it is a barrel or something. Okay. And what is their activation classification? It looks like that. Given some images, there are some human or peoples on the image, and what are they doing right now? Okay, so let's enlarge the label. You can see this is a riding horse and playing instrument, and they are running. And the latest part of the Pascal VOC challenges body layout. Given images, there are some people and they want to recognize the body part of those people. So you can see the face, and again, let's enlarge the image. There are hand, this is a head and foot, right? And okay, so let me tell a story. So, who is the organizer of the Pascal VOC? He is a researcher at Oxford University, and he did the Pascal for several years. But however, he is a young man. But however, unfortunately, he died very. He died by some reason. Okay. Therefore, as I do I see? Okay, no, sorry. So therefore, to memorize him, the ECCV conference every 2 years will give a word using his name. Okay, to some teams or researchers who contributed to the image recognition problem. Okay, so here you can see the challenge stops in 2012. Okay, at the same year, there's another important data set that was widely used. It's the ImageNet. So let's take a look of some examples of the image. So let's compare the ImageNet and the Pascal VOC dataset. The first difference is scale. There are 1,000 classes in ImageNet, but there are only 20 classes in the Pascal VOC. So ImageNet is quite variant. And there are 1 million images just for the recognition challenge. And for Pascal, the image size is around maybe 20K or 30K, relatively small. So ImageNet, when it was released, it soon became the new target of many image classification algorithms. And okay, then I will also show some, use this image to show the variance of the ImageNet. So first is object scale. So while some objects are small, like a candle, and some objects are very large, like a spider web. And the image clutter, it means some images are very simple. For example, the campus, you do not see, the background is pure. But if you see still drawn, there are a lot of objects in the image. So it gives us a message. ImageNet is really complex as the real world cases. And when ImageNet was released, Pascal VOC was the state-of-the-art algorithm. So they compare ImageNet with Pascal VOC, and they show ImageNet contains more fine-grained classes. For example, in Pascal VOC, there is only class of bird, but in ImageNet, there are many different breeds of bird. Similarly, for cat and dog, the two classes, there are many different kinds of cat and dog in the ImageNet class dataset. So now we have the concept of the dataset. The next question would be, if you have a dataset, how would you address the problem? How would you classify images? Again, this is a long-standing question. And before neural networks, there are many existing methods addressing this problem. One of them is the bag of words method. And what is bag of words? Because the method in the beginning was developed from document classification problem. It means if you have two documents, and how do you tell the two documents belong into the same classes or not? The straightforward approaches, we can collect many words as a bag of features, and we can compare whether this document and that document share the same words, or are there frequencies for those words that are similar to each other? If they are likely to be the same class of document. So that is mean bag of words. And when we apply this method for images, so we will like something like what? If you have an object, and how do you know, this object belongs to a certain class? We separate the document or extract the features from this object to be a bag of feature or bag of word. Then when we want to classify an image, we will see for human, there should be something like an eye, like a mouth, like a nose. So there's their distribution of those features. For a bike, there should be some wheel, should be some rack, should be some something like this. So it will become another distribution. For violin, again, there should be some. So by comparing those distributions, we classify the image. And this is example. If they use the bag of word, given those images, what will they see? Here, for each page, this is very intuitive for us. Okay? But however, if you want to compare patches in images, it is relatively difficult because the dimension of a patch is already high enough. Then you will suffer from the curse of dimension. So this paper use a backup feature to classify images. They don't use patch and the intensities of a patch as their feature. They use gradient. Okay, so because gradient is everywhere, you always can find the gradients in images. Every point, every pixel has its gradient. So here, let's see some example. So when you see, every circle in the image is a gradient. If you, and the direction of the gradient is shown by the arrow. And if the gradient is larger, then the circle will become larger. So for this image, okay, they will extract some gradient as a feature. And the 4 images are the example of the Z-Rack10 dataset, like this. So you can see, find the chair and the boat and the road sign and the bike. Okay. So this is a boat, bike, road sign, and chair. So they found, I should say, they found the green circles or the red, blue circles are the key features, because I should say, related to the certain classes. What does it mean? It means what is the difference from a boat image against the other classes? It means in a boat image, they will see a lot of vertical gradients. And what will the specialty for a road sign gradient images? It means they will find many gradients along certain directions and their magnitude. So how do they do? First, the step, they extract some key points, and they use those key points to extract a distribution of feature vectors, become a histogram, and then they apply a multi-class support vector machine to classify the images. Okay, however, yes, back-of-word is approach, but the approach has a very obvious limitation. It means the geometrical relationship no longer remains. So, okay, when you see the back-of-word here, okay, it is possible, okay, I should say, what is the source image? Can it be this source image? And can it be this source image? Yes. Both of the images will generate the same bag of words. Okay. But, of course, they are quite different. We only see the statistics rather than the raw image. Okay, so another method to recognize image is called part-based model. And this example is given in our textbook. So what is part? What part means? They will recognize certain geometric, a certain part of an object and remain their geometrical information. So that is a very different approach from the back-of-word, because back-of-word totally destroy the geometric information. So here, suppose actually from this image, of bird there is a person, and we can see their parts. So this is the head, body, torso, left and the right hand, left and the right legs. So how to generate those parts? First, they apply a binary silhouette method to remove the background. So they can get the image of the foreground of the body. Then they need some algorithm to fit those body parts to this binary image. This approach has been developed for many decades, and this is the earliest body part approach. It models the human faces, and it uses a spring-like connection. So this is a hair, left eye, right eye, nose, mouth, left edge, and right edge. They use something like this. This is the Markov random field, okay, to model if the two parts, for example, the left eye and the right eye, they should not be too close, but also should not be too far away. Okay, and the nose and the mouth, the same. Okay, yeah, they should keep a certain relation, and the relation will be modeled in the VIZ term. Also, for each part, they should have their own appearance or shape or color. It will be modeled by the individual terms, so the VI. All right. Here, the authors also talk about this. It's another topic for 5-grain classification. So, what is 5-grain image classification? So, this is an example. For the first, the A column is a type of bird, the same class. And the B column is also another type of bird. As you can see, both of them are yellow. And they look like each other, but however, they are different type of birds. So here you can see at the head region, you can see the black stripe here, but in the left one, there's no black stripe. There's a pure yellow region. Okay, and the same for the C column and the D column. They look like each other, but as you can spot the tiny differences. For example, on the left one, you can see the red head at the top, but at the D column, no, there's no such a pattern. Okay, so for the 5-grain classification structure, how would you differentiate those differences? Okay. Yeah, there are some algorithms. They use the part base. Okay, so why we talk about the part base? Because here we are talking about the part-based model. To solve the 5-grain classification problem, they use the part-based method to address the problem. Okay, so this is an example. Given an image, because this paper was published in 2014, so what they use a detection algorithm called RCNN, regional RCNN. This is a detection method, state of art in 2013 and 14. So they will generate a lot of proposals. A proposal means a possible region of an object. So as you can see, there are a lot of rectangles. Each of them is a proposal. Okay, so then they will test each of the rectangle, whether it is a head of a bird or a body of the bird or the whole region. It means the head and the body and a certain background of the bird. So the first row is the whole body of the bird. And the second row is the head of the bird. So from different proposal, they will crop different regions. And the third row is the body of the bird. But sometimes the proposal is not effective. So they will see, for example, this one is see the background rather than the body of the bird. They train their network to create the correct prediction or detection region of the bird. The perfect example should cover a whole body and the head and the body, 3 parts. If they can detect the 3 parts, they will train a classifier to use the 3 parts of image to predict what the type of the bird is. Because they can extract the head, so they can compare images head by head. So if the difference occurs on the head, okay, so that they can recognize it. If the difference occurs on the body, okay, for example, this one and this one, their body looks like quite different. So they will be able to correctly recognize that. Okay. Otherwise, they can use the whole image, the part of the bird, to recognize the type of the bird. Okay, the first question was how to generate the correct predicted regions. Okay, so they need many examples or training images. In their training images, every bird has 2 parts. The first part is head, and the second part is body. So these are their training images. And so that once they given a test image, once they detect that there is a bird, they will search all images in their candidates, like this one. Find the similar cases and use the head and the body region to predict the head and the body regions of the test image, so that they can generate the head and the body region. So this is the test result. Given a test image, okay, they will use the cosine similarity to search all of the candidate image in their data set. And what is the feature of the cosine similarity? They use RCN's pool 5 feature. So what is RCN? RCN is a network architecture. And in a pool 5, they will generate something like the fully connected 6, 7, and 8. Okay, let's go back of the AlexNet. Okay, so here in AlexNet in layer 5, we still have the spatial information, but in layer 6 and layer 7, we only have a long vector, something like it. In the RCN network, again, we input an image, and the image will go through several layers, and it will become a long vector. So we use the they use the long vector to compare the similarity of 2 vectors. Then they will extract some visually similar vector. As we can see, from this architecture, as you can see, the layer at the top, it can recognize the shape. Therefore, in the RCN network, they also recognize the shape. So give this image, the top 5 highly similar bird images are these 5 images. They, yes, share the same shape as the test image, as like this one. This is a test image. They use the feature to find the top 5 highly similar image. They will get this 5. So yeah, they share a similar shape with the test image. Therefore, they can crop the head region and the body region. So so they compare the method with some existing method. So the first column is the deformable part model. It was the study for R before AlexNet. And if they remove or disable the similarity constraint, okay, they will generate a result like this one. They detect the whole image, but the body in this case was wrongly predicted. So they use the similarity constraint. It means this one. Extract the similar images and use those similar images, head and body region, to predict the body and head regions of the test image. They will get this result. Okay, so however, they also reported their failure cases. For example, in this one, yes, they recognize the bird's whole body, but the head region is wrong. And here, the whole body region is wrong because it covers too much background. Okay. So this is an example for what? For the part-based method to recognize object in an image. All right. Okay. So there is a small chapter in Aspect talks about the importance to recognize object in an image. Okay, so here, when we do the instance recognition, okay, yeah. Do you care about its text, context, or background? No. For this task, you only need to exactly know where the toy train or the toy frog is. But this is not always the case. Let's see the example image here. Okay, so what is this? Is a button, and what is this? Do you think it's a phone, a cell phone? And what is this? Do you see the person, a car, and what is this? Do you see the shoe? Okay. If you take a look or enlarge it, let's see. This pattern and this pattern are exactly the same. And this pattern and this pattern are exactly the same. Okay. So what is this? In fact, those patterns are manually generated. They want to remind. Okay, so this is a news, something like a newspaper. It's a media, NIT Tech Talk. Okay, this is some magazine or newsletter. This is an interesting finding from an NIT professor. It reminds us, well, when we want to recognize something, we use the information from the context or the scene. Okay, now let's go back to the image classification task. So as you can see, this is the top 5 error rate for the ImageNet challenge. Year by year, they developed a better algorithm, okay, to achieve lower error rate. So in the first year of the challenge, they used the conventional method. It means extract the manual feature and use some machine learning algorithm for, say, supported vector machine, random forest, etc., to classify image, and the error rate is greater than 20%. In 2012, AlexNet was released, and it significantly reduced the error rate to 16%. And then okay, so let's see the difference. So 2012 AlexNet. First, deep neural network for image classification. as we said, the architecture of LexNet is very similar to the net released in 1998. However, LexNet is larger and capable to handle large images. The emits image is only 28 by 28 pixels, but in LexNet, the image size is 224 by 224 by 3 channels. Okay. So in the next year, the Zeller and Focus. Pay attention to the two authors, Zeller and Focus. Where do they are? Okay, let's show you. In the beginning of our paper, this slide, the two, they are the same author, Zeller and Focus. Okay, because they know the network very, very clear, so they can create images like this one. And then the two authors are also the winner of the ImageNet challenge in 2013. So what did they do? They just modify the architecture of LexNet, add more channels, and change its width and height of those layers. And next year, 2014, GoogleNet and VGGNet was released. VGG is a huge network, but use only the 3x3 convolution. And the GoogleNet is a relatively compact and efficient network, and there are more layers. And then next year, ResNet was released. Next year, ResNext was released. So here, this is a ResNet, and this is a ResNext. What's the difference? The difference, so Inception module was originally proposed by GoogleNet. They insert the Inception module into ResNet and become the ResNext, and further reduce the classification error. And in the same year, there's another network called DenseNet. So let's recall. ResNet, GoogleNet, or VGGNet, all of them layer by layer. The connection from one layer to another layer, and another layer to the next layer, layer by layer. And the main idea of DenseNet is, if you have a layer, the output of layer will be used not only its next layer, but all the following layers. So it will become a dense connection. It's called DenseNet. And in 2017, SENet was published. It proposed a method to learn information among channels. Okay, so the architecture can be inserted into any kind of existing network architecture. When they insert it into ResNet, it becomes SENet. And okay, then the last year of image challenge was 1917. There's no more ImageNet challenge because those performance has be greater than human beings. So after 1917, it is the emergence of transformer. In the beginning, transformer was a method designed for natural language processing. So it is a winner of that year for English to German and German to English translation competition. Let's take a look of the transformer architecture. For the translation or language processing, there are usually two parts. The first is the encoder, and the second is the decoder. For different tasks, they will use either only the decoder or the encoder or both of them. For example, if you want to classify, and like this one, if you want to classify two documents, whether they are belonging to the same class, you use decoder only is enough. If you want to generate some sentences you use a decoder, such as Chat-GPT. Okay? If you translate one language to another, you need to use both of them. So this is an encoder plus decoder architecture. All right, so let's take a break. So here, when they created the transformer architecture, it is a language problem. It is unrelated to computer vision. But later, a few years later, okay, a computer vision community will create another variation of the transformer called the vision transformer. It will become the state-of-the-art algorithm for image classification. Here, so we just take a look over here. This is the attention module. So you can find the attention module from here. So multi-head attention. Okay, it will be used in every layer in the transformer architecture. So what is the attention? I should say, the author of the transformer, they didn't invent the mechanism of attention. It was developed 2 or 3 years ago before this architecture. But they used the attention mechanism and developed an architecture like this one. So what is this? So remember, this is a language problem. That is a visual problem. So it means given some input. So they input just a sequence of a word or something, or just a document. They want to train a neural network to predict whether, okay, this is a certain class of a document. And when they want to use the translation, it means given this is an English input, and they will generate a few words in one language to another. For example, given some English sentence, they will generate some French or German sentences in their output. Then, what is the predicted probability? It means if they have a dictionary, okay, there are a lot of thousands of words, they will predict what will be the next word with the highest probability. Once they get the next word, it will be placed at the end of output. Then, again, the input is still the English sentence you want to translate. And the output will be a partial of the sentence plus the new word. And then put into the architecture, use it to predict the next word in the translated language. So within the architecture, they need to care about not the sequential word, but the every word in the sentence. So that is the attention. It means if I have generated if I have sentence of 20 words, then if I am processing the 17th word, I do not only look at the 16th and the 18th word. I need to also see the even first, second, or third words in the sentence. That is the attention means. It will allocate a weight between every two words. So because it's very useful, as you can see, it generates the best result for the challenge, okay, in 1917. So many computer vision researchers, they want to apply the transformer or self-attention mechanism for vision problems. In this NERSC IPS-20 paper, the two researchers, they use self-attention mechanism applied to small patches. So what is this? Given a 3x3 patches, they slightly enlarge it to a 5x5 region. then use the 3x3 region as an input, because every 3x3 region there is 9 elements. It can become a vector. So once they have the vector, they can compare the vector with other vectors in the image, and they use the mechanism so that they show it can replace convolutional network, because convolutional is mean you need to find you need to use some kernel to do convolution to generate the activations in the next layer. They use the attention mechanical, so that they can compare every 3x3 patches across all images like convolution, but it equals to they have an overall perceptual field. Okay. But the problem, yes, it shows attention mechanism can replace convolutional neural. But however, they didn't show the state-of-the-art result. They only show, yes, compared with some small scale dataset, the small network, a small convolutional network, yes, they can generate a better result, but this is not a self. So it doesn't attract a lot of attention. Another problem for self-attention is, okay, let's see this situation. If I have an input sequence, there are n elements, and every element has d-dimensional, the vector of the dimension. And then if k is the convolutional network, the size of a convolutional network, let's say an example. Well, as we can see, AlexNet used the input resolution as 224 by 224 to classify images in ImageNet. And there are 3 channels. Then, how many entries do they have? They will have 224 by 224. They are totally 50k pixels in an image, and the channel of the pixels are 3. So suppose they have 50k vectors, and every vector has 3 elements. Then, okay, when they use self-attention, the computational load for this method is the order of n squared d. It will be 50k times 50k times 3. And if they use convolutional to develop a network, then their computational load will be 50k times 3 squared times k squared. So if the k is not very large, say 5 by 5 or 3 by 3, then as you can see, convolutional network will be much efficient than self-attention network. So that's the reason why the vision transformer is very important, because it solves the computational load problem. So its innovation is given an image first. Okay, say this. Given an image of 224 by 224 by 3, it first separate the image into several 16 by 16 patches. So given an image, it will separate them into several patches. Then they apply a linear projection. It equals to a convolutional network, because linear projection of those 16 by 16 patches is the same. It's like you convert them from one space to another space. Then they can get less. So here you have 50k input vector, input sequence. But here, because you crop them into patches, so the length of the input sequence are much shorter than the 50K here. Because the n becomes much smaller, the computational load for self-dimension at the order of n squared d also significantly reduced. Then they can apply the transformer encoder to train the network here, so they can generate some predicted result as the convolutional network. Okay, the key issues here. Why vision transformer is okay? Let me see their result first. The state-of-the-art convolutional network in 23 years ago is BIT. It means big transfer. It's a modified ResNet architecture. So they compare the vision transformer with the BIT. Now see the logo here. BIT is here. Okay, so you can see the range because there are several models. For example, ResNet 152 and ResNet 101. For different models, all of them belong to the BIT. So you will see a range here. Okay. And the same, the vision transformer has different models. It means the number of layers and the number of 3260 means how large a patch will be cropped. So as you can see, when they use 1.4 million training images, convoluted BIT generate a better performance than any type of vision transformer. But if they increase the number of training images from 1.2 millions to say 100 millions, okay, then some vision transformer generate better results than BIT. And if they use the JFT dataset, it's a Google's private dataset. We cannot access, but there are more than 300 million images. Use so much image, and as you can imagine, how many machines are required to generate the experimental results? Huge, extremely huge. However, their largest vision transformer module, the VIT, huge, and it generates best performance than the BIT network. Okay. So here you can see if they not use the dataset, but use a certain type of training images extracted from the JFT 300 dataset. Okay, then they found the same case. So first, this is the ResNet 152. This is this curve. Okay. Well, when you're training image, if you have 10 million or 30 million training images, it works better. But if you increase the number of training images to 100 million or 300 millions, then the blue curve is the result of the vision transformer large 16. Okay, it generates better results than BIT. So what does it mean? Vision transformer is more powerful, but you need huge training images and huge computational resources. So why vision transformer is better in that scenario? Okay, the reason is the inductive bias. So what is the inductive bias? It means if you have a model and you use the model to predict something or generate some result, you have some assumption. And the assumption will be fixed or embedded in your model. And okay, let's see. What is the assumption for convolutional neural network? The assumption is nearby pixels are more important than faraway pixels. Why? Let's talk of this is the network of AlexNet. And when you do convolution, what information do you get? For this convolution, you only get the information nearby. You won't get the information from far away pixels. And again, when you do convolution here, you won't get information from here. So when you add the depth of the network, you will increase the perceptive field. And however, if you want to see the relationship between one pixel to a far away pixel, usually it will happen in the deeper layer. But at that time, too much information are mixed. So you will pay less attention to care about pixel or information far away. So that's the CN's assumption. Nearby pixel or nearby region, they are more important than far away pixel. So let's take a look of this image. You will get a sense. Okay, so when you see this pattern, you only care about its nearby pixels. You won't pay attention to something far away. Even when you have the layer 5, okay, when you see this, okay, you only pay attention to its local structure rather than its far away signal. That's the inductive bias for neural network. So, okay, in this paper, they show an interesting result. Okay, so here, what's the okay, so let's use this example to show CN's inductive bias. This is the skin of an elephant, and of course, this is a cat. Okay, if they combine the texture of this elephant and the shape of the cat, they will generate this image. And what will be classified by a neural network for this image? Well, it will be classified as an elephant. What does this mean? It means the neural convolutional network pay more attention to local information. It means the texture rather than the shape, because the shape of the cat is quite far away around the image. So they also show this example. It means given an original image, they try different networks. AlexNet, GoogleNet, VGG, ResNet, okay, all of them are the winners of the ImageNet challenge. And if use grayscale, fine. Those networks and even human beings can correctly recognize the image. If it uses silhouette, then okay, it drops significantly. If they use age, okay, it further drops significantly. But if you use texture or every CN networks generate very good results. So that's the evidence to show the inductive bias of convolutional network. Okay, as a result, from this paper, okay, the computer vision community pay attention to vision transformer, because if vision transformer is more powerful than convolutional neural network, why not use it? Therefore, from 2011, 3 years ago, you will find a lot of papers. They compare their results. Okay, when they develop a new method, they will try vision transformer and a convolutional network at the same time. So from this paper, this is the paper of Dino. I don't know. Okay, fine. So this is the table 3 of the paper of Dino. Okay, so as you can see, they try different backbone. One is convolution ResNet 50, another is vision transformer, and they found yeah, vision transformer generate better perform result. Okay, and this is CLIP. CLIP, as we see, this is a contrast learning for language and image. They also try two backbones. One is their CLIP method using vision transformer, and another is their CLIP architecture using ResNet. And they see, okay, so this is the vision transformer, and this is the ResNet. This axis means how many computational load for a single image. So under the same computational load, vision transformer performs better recognition rate than image than ResNet. And then they not test on a single dataset. They compare the result on 27 image classification datasets. All right. So the message here is, okay. After 3 years ago, there is a paradigm transform from convolutional network to vision transformer, right? And then, okay, we are talking about the application for image classification. If we can do image classification well, or what can we get? One is the example mentioned in our textbook is the GrokNet. Okay, it is the network developed by Facebook. What can it do? It means given an image, it can extract objects from the image and then do image classification. Then it can recognize, okay, this is a certain type of class. Then what? It can, okay, this GrokNet is not well known for most people because it was designed for a commercial purpose. As you know, Facebook is a company, right? And there are a lot of users of Facebook. When they see some image on Facebook, what kind of advertisement should they see? So Facebook need to develop a method or algorithm so that it can recommend their I should say to insert the proper advertisement to their users so that they can make money from their clients. So when I search this paper, the citation of this GrokNet is very low, less than 1,000. Okay. However, I think Facebook or many big companies like Google, when they measure income comes from advertisement, they need such a image classification network to foster their business. All right, let's take a look of the dataset used by the GrokNet. They developed a dataset covering those objects, home, product, home attribute, fashion, vehicle, or some search query. Search query means when they use some search engine, even the Facebook, they have their own search engine. The users query some image, okay, and they will show a list. Which is the one the users really want depends on which image or which link they click. So that is the meaning of the search query. They compose a very large dataset containing 89 million images, and there are 83 losses. Okay, so why do they need to create such a huge dataset? Because there are many long tail, or we say low frequency images in the world. They still need to cover those images. Okay, so they build the dataset. They create a network use the ResNet. And once they create the architecture and use their huge data set to train a network, they generate the result like this one. And once a user take a picture or upload it to the Facebook can insert or recommend their clients to provide some advertisement for the Facebook users. Again, I should say another. Well, Facebook has a very effective image classification algorithm. Does Google has another copy? Yes, of course. So the left one is the Google Lens. If you use an Android device, you can find or download this app into your cell phone. This is very useful. For example, this is the application. You can use Google Lens or something similar. Okay, Google Lens is a built as a should say product provided by Google, and there are many similar apps provided by other companies or some universities. They can recognize flower, plants, something in the world. So if you go somewhere, go to a park, and you don't know what the flower is, use your cell phone. Okay, it will execute the image classification algorithm to tell you this is what the name of the flower is. And also this Google Lens is the app for mobile devices. If you use laptop or desktop through a web user interface, there is a Google image web page like this one. You can upload an image to the service. Then it will show the same classes so that you can see, okay, it will show here from this search the result. It is the wood duck, right? So this is the application for generic image classification. And now let's talk about a domain-specific image, that is human faces. Given those images, can you recognize who they are? Okay. No. Any one of them is okay. Now I will show their names. Okay. 1, 2, 3. Show. Okay. Michael Jordan, Bill Clinton, Tom Hanks, and Saddam Hussein, Elvis Presley, and Prince Charlie. Okay. Richard Nixon. Okay, so what does it mean? It means we humans, we can easily recognize human faces even though they are in a low resolution. Okay. So there are many existing human recognition data set. So this is a CAU multiply, and this is labeled face in the wild. And this is mega face. So the importance of mega is it is the first data set having more than 1 million face images, right? So let's take a look. Oh, of course, our textbook doesn't cover the Celeb A data set, but it is also very famous because, okay, well, it contribute a significant impact of the community and won the Everhand Prize 26. So what is who is the Everhand? Okay, so the Everhand is the organizer of the VOC Pascal. Okay, so let's take a look at the VOC Pascal. So this one. Everhand organized the VOC Pascal. So he's a main contributor. But however, unfortunately, he died very early. So to memorize him, okay, there is the okay, Everingham Prize award for good contribution in the community of computer vision. Okay, so let's talk about another story. Last year, one of the team in our computer vision classes want to develop an algorithm to recognize human faces under extreme lighting conditions, like this one. So are they the same person? Yeah, yes, of course. From its shape and the background, yeah, of course. But what I want to say is the lighting condition of the face is extremely unfriendly. How to recognize these faces under this scenario? That's their problem. They want to solve the problem. Okay, so let's take a look. The first data set in the list, CNU multi-path. So I should say, the team, they want to use CNU multi-path to develop the algorithm because the CNU multi-path, it covers several different illumination conditions. So let's see the features of the CNU multi-path. CNU is a Carnegie Mellon University. As you remember, in our previous week, we see they developed a studio, very impressive. The same. When they try to compose a data set of human faces, they create this one. It means given a face, they can take 15 poses and let's see the number. Okay, so they can take 15 poses and 18 different flashes. Why? Because they have a studio. AV yellow circle here is a camera, and the AV white square here is a flash. So in the studio, as a subject sit on the chair, okay, they control those camera and the flash. They will get the result like one. So they are different illumination conditions. So they want to use the dataset to develop the algorithm can overcome this extreme lighting condition. There is another factor called season. It means when a subject was taken the photo, okay, several months later, how much change will occur to the same person? And a few months later and a few months. So to compose this dataset, they use a whole year to generate those images. They also provide some high-resolution version and different facial expressions. So this is a huge dataset. The total there are more than 300 gigabytes for the whole dataset. All right, so okay, now let's talk about once we have the dataset, there are some famous methods proposed in the history, okay, to manipulate human faces. So let's take a list one. It was published in 1995, almost 29 years ago. Their idea is quite straightforward. They only manipulate two factors. One is shape and another is color. So how do they do? First, they collect 61 female faces and 43 male faces, and we align them to generate the average face image, this one and this one. So they can extract their edges as their shape and compare their colors to get the color differences. So give this input image, so the second color, they can adjust their images by the factor gender, because from compare with this image and this image, what do you see the difference? The lip becomes redder, and the skin becomes yellower or something else. Okay, so again, this is a male subject, so its lip becomes palmer or something else. Okay, and this is neutral, means between the two gender. This is you cannot clearly see it is a male or female faces image, and they can switch the gender and even enhance the direction of the gender. So this is the first, I should say, famous method published in the history. And then 2 years later, here they manipulate the face, and the model is very simple because there are 103 sample points in the space. Okay, let's just calculate the mean of those two classes. If you want to model the face images in a another way, okay, so this is the eigenface. Well, eigenface means given a set of training images, they treat every image as a vector. So this is a high-dimensional vector, like this one. This is an illustration for only 2 dimensions. Well, from this distribution, they can find the principal component. In this case, the principal component is the first axis is this one, and the second axis is this one. They can project the image. For them, it's just a vector to those principal components. It means those axes, orthogonal axis in the high-dimensional space, they will generate the projected result. From this example, this is a given input image. The first eigenfaces, it means the first projected image on the 8 principal components are the 1, 2, 3, 4, 5, 6, and 8. So it means given a face image, they decompose it into 8 different axes. They can use the 8 component image to reconstruct a certain type of images and reduce the dimensional of the vector. Okay, so this is another example. Oh, this is an active appearance model. What's the difference from the eigenface and the active appearance model? It uses landmarks. So from these images, you can see there are totally 68 landmarks on the main features, on the eye and the mouth. Let's enlarge it. Okay, here, so there are some key points. Okay. So when they collect a bunch of data and label of them together, they can learn the shape and the textures of those face images. So let's see this. The second column are mean. So the 1, 2, 3, 4 are all the same. Like the eigenface, they also learn the principal component for those 68 landmark points. Though they will have several axes, the first, second, third, and fourth. And they apply the change from the mean face to along a certain axis. So this is the -3 standard deviation, and this is +3 standard deviation. So you will see the change of the face. So as far when I see this, I guess the first axis will change the length of the jaw. So you see the jaw is much shorter here, and the jaw is much longer here. And the second axis, I think it is the orientation of the face. Okay, so this is neutral, but it is slightly turned right, and another is slightly turned left. And from this axis, I guess it is the size of the eyes. So the eyes here are quite larger than this axis. So this is another way to manipulate the face image. Face image is a specific domain of generic images. Of course, when you can manipulate the face image in 2D, of course you want to manipulate it in 3D because this is a 3D world. So the 2D cases is like this one. It is the special case for the 3D cases. And look, I should say this paper was published in 2001. And 6 years later, they proposed their 3D method. So this is an improvement. Once you reach achieve certain milestone, then okay, the researcher groups always think, oh, how can I make a breakthrough to generate better results? Okay, so let's see. Okay. So I should say, who is he? In fact, he is a professor at the California University. Okay, so when you, I can say, this multiply, right? This person is the same as this person, the same one. Okay. So what I say is, I think California University, the researchers in the university, they do study for analyze human faces for a long time. So they created the CNU multiply and also created the 3D AAM model. Oh, by the way, I want to talk about this. As you can see, there's many data sets. And why celeb A is so important? Because it is free. Everybody can download it for free. However, CNU multiply is not free. If you want to get the data set, you need to pay for it. So okay. I don't know. I don't know how much it. So that's a problem. When your students in previous year, they asked me, why can I not download CNU multiply? I told them it's because it's not free. You need to pay for it. But however, I have it. If you want, I can share it with you. Okay. I have it because one of my paper, I use CNU multiply. And my advisor, he is the friend of he. So he can get the CNU multiply for free. Okay, fun. All right, so what I want to show you is they find an algorithm to fit the 3D active model to a human faces. Therefore, in the initial, it is not well aligned. And after a few iterations, it will go cover the human faces. And then more iterations it will fit the human faces. Okay, so that is the result of 2007. Then 2014, deepface. Okay, deepface was mentioned by Ann Chen. Okay, but I want to slightly. Okay, so you need to have the impress what it is. Okay, I should say this is the library. I should say that there are two deepfakes. One is algorithm, and another is a Python package. They all call deepfakes. And if you use the Python package, it covers not only the deepfakes. It will publish in CPR14. It also covers VGG face, FaceNet, OpenFace, etc. All of them are face recognition algorithm. And okay, let's see the deepfake at first. Well, it developed, as you can see, in 2012, AlexNet was released. Okay, so this is an explosion of a network. So in 1914, they developed a neural network-based face recognition algorithm. There are only 9 layers because in 1914, when Alex VGG and GoogleNet was just released, and 1 year later there will be the ResNet. The depth will increase to 152. However, there are 4.4 million faces image. In that year, that was the biggest one. Why? Because the team is from Facebook, and there are a lot of face images available in Facebook. So they created a network only 9 there, but it's called deep face because it did enough in that year. And they generate a very, very good performance on the LOFW data set. So what is a LOF? Label face in the wild. It is this. Okay, just the second one, faces in the wild. So you can see the LOFW, the terms here, label the face in the wild. So let's take a look at how it works. Given an image, you need to first crop it, then apply the 2D models to localize those landmarks, and then use a 3D models to transfer the 2D models to a 3D, so you get the 3D mesh. Once you get the 3D mesh, you can rotate or manipulate, change the 2D faces to the upright frontal faces. So this is the upright fronces, and this is not used. When you have the upright fronces, you can apply their neural network to predict or to present the image. So from this image, you can see when it converted to the upright frontal faces, you will see the same direction of the two eyes. They are pointed to the right. And this region is extended to this region. Okay? Then they just apply the 9-layer network to predict their results. And in that year, 97.35 is the best performance. But how about other methods mentioned in the deepface package? Let's take a look. So this is a survey paper published 3 years ago. There are many face algorithms compared together. So our deepface is here. So you can see the accuracy on the label, the face in the wild is 97%. But soon, there are a lot of faces recognition algorithms reach 99, even 99.83. Okay, so this is a so we can see VGG face is here, and deep face is deep eye. What is the other? Okay, fine. But I only see the FaceNet is here. VGG face is here. Okay, so from this survey paper, we can still see. Okay, this is the why there is a significant, I should say, gradual improvement, because they use different loss functions. In deepface, they use the softmax loss function. It looks like the one. It means if those face images belong to different classes, if they are wrongly classified, then we penalize it to modify the weight of the architecture. But when they try to use different losses functions, for example, the trip loss is used by, okay, it means if you have 3 points, 2 of them are similar to each other, and another one is different from the 2, then you should let the 2 similar one close to each other and enlarge the distance from the third one to the other one. So this loss function is more useful than the softmax loss function or the cross entropy loss function. And they even introduced some new loss functions, like this central loss. I'm not sure what is that. But however, when they tried different methods, they found, okay, it is more useful to correctly classify human faces. And human face, what is human face? It's a specific class of images. Right? Do you have any question? Okay, no. If so, thank you. So this is the end of the course today.